Okay, in this video, I'm going to go through the OCR A-level chemistry paper. This is the paper 1, periodic table and physical chemistry. And this is the 2020 paper, and this is the second half. I covered the first half of the paper in an earlier video. Okay, so first question is about weak acids, methanoic acid and ethanoic acid. A student reacts magnesium with an aqueous solution of ethanoic acid and a redox reaction takes place. Right, so this is very similar to the reaction if you think about how magnesium would react with any acid, like for example, hydrochloric acid. You're going to get magnesium chloride and H2 gas. Okay, and so ethanoic acid is just like HCl. It is a monobasic acid. You've got one proton, right? So instead of the chloride ion here, we're going to end up with the ethanoate ion. Right, so the formula of magnesium ethanoate is going to be MgCH3COO twice, and of course the magnesium there is going to be the +2 ion in there. Okay, so the equation there, let's write that down. Then we've got Mg plus 2 ethanoic acids goes to magnesium ethanoate and hydrogen gas. Okay, explain in terms of oxidation numbers which elements have been oxidized and which have been reduced. Well, if you look at the magnesium here, it's got a 0 oxidation number, whereas in the magnesium ethanoate here, it's a +2. It's a magnesium +2 ion. So the magnesium has become oxidized. And you can probably see it's the hydrogen that's been reduced there, because the hydrogen in a compound, right, that hydrogen there has got +1 oxidation state, whereas in the element is obviously 0. So the hydrogen has been reduced, okay? Right. So they give us the Ka values of methanoic acid and ethanoic acid. Now, we need to see what happens when we mix the two acids together. Now, it's important to realize which one is the stronger of the two weak acids. And we can do that by looking at the Ka value. Okay, so we look at Ka there. You can see that the bigger the top bit is, H plus and A minus, the bigger the value of Ka. And of course, if you've got higher values of concentrations of H plus and A, you've got more dissociation. So the bigger the Ka is, the stronger the weak acid. So we can see from that ethanoic acid, methanoic, this one here, is the strongest. So that is going to end up protonating. That's going to lose a proton and give a proton to the ethanoic acid. So the equation that's going to happen there is we're going to form, that's going to lose a proton, and the ethanoic is going to gain one. The ethanoic acid actually behaving as a base there. To form that, we stuck a proton on it. Okay, and label the acid conjugate base pairs. So this one, this is an acid, we'll call that acid 1. And its conjugate base is the methanoate ion here, that's like base 1. Here, the ethanoic is behaving as a base, so let's call that base 2. And if the reaction went backwards, it'd be this species here, which would be acting as the acid, so that's acid 2. Right. Answer the following questions. Okay, the student measures the pH of ethanoic acid as 2.72. Show that the concentration of the acid is that. What we need to just remind ourselves the Ka of ethanoic, and that was 1.78 times 10 to the minus 5 or per decimeter cubed. Okay, so I'm going to write down what happens when that acid dissociates. HA goes to A minus and H plus. Right, let's write down the start concentration and the equilibrium concentration. So that's the start concentration is before the acid HA has had a chance to dissociate. Right, we don't know the concentration of that, so let's just write down HA. We've got to prove later on that that's got to be 0.24, but let's pretend we don't know what it is. And we'll say that we've got 0 A minus and 0 H plus, because we've always got a tiny bit of H plus, but in water, we can ignore that. Now it tells us that the final pH is 2.72. So the final H plus concentration is equal to 10 to the power of minus pH, 10 to the power of minus 2.72, which is equal to that's equal to 1.905 times 10 to the minus 3. Okay, so concentration of H plus is 1.905 times 10 to the minus 3 at equilibrium. Now the concentration of A minus has got to be the same, because 1 mole of A minus, gives you one, and you get 1 mole of A minus every time you get a mole of H plus. So that's the concentration of the A minus also. The concentration of HA is going to be that minus this number here, but I'm going to ignore that because that is much smaller than the concentration of HA, so it's negligible, so we can just ignore it. Right, now we need to write down our Ka expression. So Ka is equal to H plus A minus over HA. We want to find out what the HA concentration is, so let's rearrange that. HA is equal to H plus A minus over Ka. Put the numbers in there. So that's 1.905 times 10 to the minus 3 all squared, divided by the concentration, divided by Ka, which is that. And that works out to be 0.204 dm mole per dm cubed. So we've proven what we're supposed to prove, that is the concentration of that. Okay. Right. Now here's a bit more difficult. We're going to make a buffer solution. Okay, from ethanoic acid on sodium ethanoate. Right, so the student mixes some of the weak acid, okay, with some of its conjugate base. Okay, calculate the concentration of this solution needed to prepare this buffer solution at pH 4. Okay, so what I'm going to do is I'm going to rearrange the Ka expression so that we get H plus concentration is equal to the concentration of HA. Let's put Ka first. It's equal to the rearrange that, we get Ka HA conc over A minus concentration. Right. So I'm going to then say, right, so the hydrogen ion concentration, well, what's the concentration of HA? Is obviously the moles of HA over the volume, V, which is, I'm just going to call it V, because I'll cancel out those V's. There's actually 1 dm cubed, that volume, but we don't really need to know what it is. So Ka is equal to moles of HA over V divided by the moles of A minus over V. Those V's are going to cancel out, get rid of that and that. So now we've got the H plus concentration is equal to that. Now we need to find out the moles of A minus. So I'm going to rearrange that equation to give us moles of A minus. So the moles of A minus is going to be equal to Ka multiplied by the moles of HA divided by the concentration of the hydrogen ions. Okay, Now we're in position to put some numbers into that equation now. What do we know? We know Ka. We know H plus because we know the pH. And we need to work out the moles of HA. Now, the way we work out the moles of HA, because we know it tells us here we mixed 400 centimeters cubed of a concentration of that of HA. Okay, so let's write that down. Moles of HA. It's concentration times volume. The concentration was 0.204, and we have 400 centimeters cubed. That's 0.4 dm cubed. Okay, that is equal to 0.0816 moles. Right, now let's work out the concentration of H plus here. H plus is equal to 10 to the power of minus pH. That's equal to 10 to the power of minus 4. pH 4 is the pH of the buffer. Let's put those numbers in to work out our moles of A minus then. Moles A minus, the Ka, which is 1.78 times 10 to the minus 5, multiplied by the moles of HA, we just worked out in green over there, it's 0.0816, divided by the hydrogen ion concentration, 1 times 10 to the minus 4. Put those numbers into a calculator, we get 0.01452 moles. Okay, so that's the number of moles of the sodium ethanoate, but we need to work out the concentration of it. Okay, now we're making the solution by mixing 600 centimeters cubed of that sodium ethanoate. Right, so the concentration of sodium ethanoate conc of the Na. Sorry, let's write it down properly. Is equal to the moles over the volume. Which is equal to 0.0816, and the volume is 600 centimeters cubed. That's 0.6 dm cubed. So the concentration required is 0.0242 moles per decimeter cubed. That is our final answer. My buffer calculations are difficult. I've got, if you go to my homepage on YouTube and look at playlists, there is a whole load of videos on buffer calculations. If you have a look, there's a whole playlist of them. Okay, so that is our final answer, 0.0242 moles per decimeter cubed. Right, now onto standard electrode potentials. Okay, right. So we've got 4 reactions and the electrode potentials are given for them. The student sets up a standard cell based on redox systems 3 and 4. Draw a labeled diagram to show how we could set this up to measure the standard electrode potential. Okay, so the convention is to put the most positive on the right. So we're going to put the manganate system on the right. Okay, so I'm going to draw, I've got 2 beakers. That's the left hand, that's the silver one. And here is the manganate one on the right. We're going to have to, let's see what, we're going to have to connect them with the salt bridge. There's your salt bridge there in blue. Right, let's look at the right-hand side one, the manganate one first. Okay, what ions have we got in there? We've got manganate ions. So we want manganate, that would be potassium manganate 7. And the concentration of that should be 1, is it standard conditions? It should be 1 mole per decimeter cubed. You're also going to have some Mn2 plus ions in there. That's probably manganese sulfate you'd use for that. And that's got to be 1 mole per decimeter cubed as well. And you'd also need some acid in there. So you want H plus ions, probably use sulfuric acid. So the H plus ion concentration is 1 mole per decimeter cubed also. Right, and we need something to connect that, and there's no metal there, so we need a piece of platinum. On the right hand side, right, we're going to have here we've got silver ions, Ag plus, 1 mole per decimeter cubed again. That will be silver nitrate probably. And you need a piece of silver metal in there to make the connection. So that's Ag metal. Yeah. And now we need to connect them with a high resistance wires and a high resistance voltmeter. That's a high resistance voltmeter, so you don't get any current flowing. Okay, and that will enable you to measure the standard cell potential. Okay. Now we're going to have to use those cell potentials there, I think. Okay, so I've copied them again. I've copied the table out again so we can see it. Okay, a student warms a mixture of methanol and acidified potassium manganate 7, and you see bubbles. Explain its observation. Okay, right, include equations in your answer. Okay, so let's have a look. What we need to look at methanol. So where have we got methanol? We've got it in this one here in system number 2. Okay, and we've got manganate, so we're interested in this one as well. Now, this equilibrium is more positive than number 2. So that is going to be best at taking in electrons. So in other words, that one is going to, taking in electrons, is going to go forwards. That's going to go forwards, and it's going to force equilibrium 2 to go backwards. So we've got methanol there, that's methanol, and that's going to be oxidized to methanoic acid. We can probably see that's not the end of the story, because in system number 1, we've got methanoic acid there, and manganate is considerably more positive than this one as well. So it can force this one to go backwards. The manganate can oxidize the methanoic acid even further to carbon dioxide, and that is the bubbles you're seeing there. They're the bubbles. Okay, so that is the bubbles. Explain the observation. Okay, we've got the bubbles of carbon dioxide, and we've explained it in terms of those, and we need to include an overall equation now. Okay. Right, so we're going to have so we're going to have manganate, MnO4 minus, the overall equation, and that is going to react with methanol to form carbon dioxide and Mn2 plus ions. Okay, but we have to be careful with the number of electrons here. Okay, so the manganate is being oxidized by 5 electrons. Let's have a look at the methanol. Right, the methanol first of all is being oxidized by 2 electrons, and then it's oxidized again by another 2 electrons. So the methanol is by 4 electrons. So what we're going to have to do is we're going to have to multiply till we get 20 electrons. It's going to have to be 20 electrons. So it's going to be a pretty funny equation, this one. So we're going to have to multiply this one by 4 and multiply this one by 5. Okay, so let's write down those So we're going to have the 4 manganate into 4 Mn2 plus. We're going to have 5 of those going to 5 CO2s. And now we're going to have, let's just check our oxygens first of all. We're going to have some waters and some H pluses. Let's see where they go. So on the left-hand side of the equation, let's see how many oxygens we've got. We've got 16, 4 times 4, 16 oxygens plus 5 there. That makes 21. Right, so that gives us, so we've got a total of 21. And we have only got, well, 5, we've got 5 times, we've got 10 there. So that means we are missing 11 oxygens. Let's check that. How many we've got? 16 plus 5 here on this side is equal to 21. We've only got 10 on the right hand side. So that means we've been missing 11 oxygens. So we're going to have 11 H2Os here. And that means on the right hand side of the equation now we have got 11 H2Os. So that means we've got 22 H pluses, whereas on hydrogen, sorry. Whereas on this side of the equation, well, we've got 10 hydrogens here. So that means we are missing 12 H pluses, so we need 12 H plus there. Okay, that is the final equation. Right, okay. Right, methanoic acid can be used as a fuel cell. And the fuel cell is supplied at one electrode and the oxygen at the other electrode. The standard electrode potential is 1.34 volts. The overall reaction, so that's the overall reaction is shown below. Right. Using the information, deduce the half equation for the reaction of the oxygen. Okay. So right. Well, let's look at the overall equation. We can see that the oxygen goes to H2O. So I'm going to write down here, the other one is going to be half O2 goes to H2O. And we need to balance that with H pluses. So that means we're going to need 2 H plus on this side of the equation. Now we need to balance the charge. That means we're going to have 2 E minus. Okay, that side. Right, and this must be the most positive one, because this one is going to take in electrons. It's got to go forward, okay? That's got to go forwards. And this one, the methanoic acid is going to be oxidized to CO2. That's going to go that way. And we know that E cell is equal to the E right minus the E left. Now the right hand side should be the positive one. So this is the right electrode, the right hand side, and this one is going to be the left. So we need to find out the standard electrode potential of the right. So let's rearrange that. You get E right is going to be equal to E cell plus E left. Right, E cell, they tell us, is 1.34 volts. And the left-hand side electrode is minus that, 0.11. And that is equal to, so we work that out, we get the right-hand side electrode is 1.23 volts. Okay. So deduce the half equation. That's that in green there, and the E value of that is, just worked it out, plus 1.23 volts. Okay, so this is about rates of reaction now. Investigating the reaction between ethanoic acid and methanol in the presence of an acid catalyst. The equation is shown below. Okay, so that's the esterification. Carry out experiment to determine the order with respect to the ethanoic acid. So they use a large excess of the methanol, so that essentially stays constant. Okay, and the temperature is constant, which is obviously. And the students taking a sample every 20 minutes and determine the concentration of ethanoic acid in each. Okay, they don't say how they do that, but they take it out every 20 minutes and do it. And they plot the results on the graph below. Okay, so we can assume that because the methanol is in large excess, the concentration of methanol is not changing. So any change in rate is just due to the change in the concentration of the ethanoic acid. Okay. Right, it says here, explain why the student uses a large excess of methanol. Well, so that essentially the methanol concentration is so big that it doesn't change. And we need to do that because we want any change in rate to be down to a change in the concentration of ethanoic acid. So we need to keep that constant. Okay, then next question, what does it say? Use the half-life of this reaction to show that the reaction is first order with respect to that, and show you're working on the graph and below. Okay, right, so let's do that. Now, for a first order reaction, half-life, T1/2 is constant, isn't it? Yeah. So we need to show that's constant. What is T1/2? It's the time taken for the concentration to drop to half of its value. The concentration of ethanoic acid to half. Right, so let's see, the concentration of ethanoic acid is 5 times 10 to the, yeah, up there. Let's see how long it takes to drop to 2.5 times 10 to the -3, which is going to be there. Oh, we need to draw a line of best fit there, I suppose. Let's do that. You can see it's not, if you get a ruler on that, you can see it's not, it is actually a curve. It looks a bit linear, but it's not. Okay, it's a curve. Right, so let's see how long it takes for to drop from 5 to 2.5 times 10 to the -3. Well, that is taking almost exactly 100 seconds. So T1/2 there is 100 seconds. Normally, what we'd do then is see how long it takes to halve again down to from 2.5 to 1.25. But that is somewhere over here. Yeah, so we can't do that. So let's see like the time taken to drop from 4. Okay, here's 4. That's when it's 4 times 10 to the -3. How long it takes to drop from 4 down to 2. So that is about there. So we can see how long does that take? Well, that's about 135 seconds there. And this one is 35 seconds. So the time taken, 135 minus 35, once again, it's 100 seconds. So T1/2, second time we measured it, that's 100 seconds as well. So the half-life is always 100 seconds, so that means it must be a first order reaction. Okay, now I think I've done that graph again. Determine the initial rate of reaction. Yeah, I've cut the graph again because, right, how are we going to measure the initial rate of reaction? Well, you measure the gradient, the rate is equal to the negative gradient. It's got to be negative because it's the disappearance of the reactant rather than the appearance of the product at time 0. So I haven't bothered drawing the curve, but I've just drawn the tangent because you can see that red line is the tangent essentially at time 0. So it's like kind of straight in locally, that line is straight, isn't it? There. So we just need to measure the gradient of that red tangent. So the gradient is going to be the change in the y over the change in the x. The change in y is going to be 5 down to 2, but that's 5 times 10 to the -3, minus 2 times 10 to the -3, and the change in the y, that's the that's the time, so that's that yellow line there. That's going to be what? That's 132, is it? Let's see, what is that? That's not 132. That's 100, and that's 110 there, isn't it? It's about 112 divided by 112 seconds. That's naught time there. Okay, put that into a calculator. What do we get? We get 2.68 times 10 to the minus 5, and the units are concentration per time. Yeah, mole per decimeter cubed per second. That is our answer there. Okay, then the student carries out a second experiment, this time looking at Kc rather than the rate, the equilibrium rather than the rate of reaction. Okay, so it mixes 9.6 grams of methanol. We need to work out the number of moles of that, which I've done there. So that 9.6 over the MR, 32, that's 0.3 moles of methanol. And they mix that with 12 grams of ethanoic acid there. So that's moles over MR again. To work out the number of moles, we've got 0.2 moles of ethanol. Right, so we need to fill in this table here: start moles, used up moles, and equilibrium moles. Sort of fairly standard way of doing these. Okay, so let's put that in. So start moles of ethanoic acid, that's 0.2. Start moles of methanol is 0.3. We've got 0 ester and we've got 0 water at the start. And at the end, they tell us we've got how much? We've got 0.03 of the ethanoic acid left over. So that means we must have used up 0.2 minus 0.03, which is 0.17, isn't it? We've used up 0.17 of that. Now, if we've used up 0.17 of that, we must have also used up 0.17 of the methanol. So how much methanol have we got left over? We have got 3 minus that, which is that's going to be 0.13. Now, if we've used up that many moles of ethanoic acid, we must have made that much ester, that much water. So that's going to be 0.17 there, moles of the ester, and 0.17 moles of the water there as well. Let's put those numbers into our Kc expression, which we've got in black down here. So Kc, and now, let's do that's the moles, and we should really do concentration. Now we don't know the volume of this, but we can say the equilibrium concentration then is moles over volume. So that's 0.03 over V and 0.13 over V, and these V's are all going to cancel out because we've got, it doesn't always cancel out, but it does when you've got the same number of moles on both sides of the equation, which we've got here, and so they'll all go. So we're going to put the Kc is equal to 0.17 over V all squared divided by 0.03 over V multiplied by 0.13 over V. Okay, so Kc is equal to, those V's are all going to cancel out, and Kc works out to be 7.41. I think we should really give that to 2 significant figures because all our data is to 2 sig figs, so that's going to be 7.4, and there are no units for that because you've got the same number of moles on both sides of the equation. So there is our answer there. Okay, now onto an inorganic question here. So they've got bromine in organic solvent. Okay, bromine in organic solvent, that's going to look orangey red. They say orange, yeah. And it is more soluble in the organic solvent than it will be in the aqueous layer. And they've got aqueous sodium chloride to one test tube, and sodium iodide to the other one. Okay, let's see what's happening. When you add bromine to sodium chloride, then let's explain how the student's result provide evidence for the trend in reactivity of the halogens. Okay, and write ionic equations for any reaction that takes place. Right. So first of all, let's do the reaction with the sodium chloride. Well, there's no reaction there. So with sodium chloride solution, the organic layer remains red or orange. And why is that? It's because the Br2 has not reacted. Why hasn't it reacted? Well, it hasn't reacted because bromine is not a good enough oxidizing agent to oxidize chloride ions to chlorine. That doesn't happen, okay? And if it did happen, of course, the red-orange color of the bromine would disappear, and because you'd have the colorless bromide ions. Right, that doesn't happen. Bromine is not a good enough oxidizing agent to oxidize chlorine. The reason why is because bromine is compared to chlorine, it's a bigger atom. That means the outer shell of electrons are further from the nucleus. Yeah. So it's harder for bromine to attract an electron into the outer shell than it is for chlorine because it's further from the nucleus. Obviously, the nucleus is positively charged. Okay. Now let's do the other one with sodium iodide. Right. So when you react it with sodium iodide, right, you do get a reaction there. I2 is made. Okay, that is more soluble in the organic layer, so it's going to dissolve in the organic layer, and I2 is violet in organic solvents. So you've made iodine. So the equation that's happening there is you've got Br2 plus 2I minus in aqueous solution goes to 2Br minus, so your orange color disappears because you form the colorless bromide ions, and you form I2, which is purple in organic solvents. And again, why does that happen? Well, it's because iodine bromine is a better oxidizing agent than iodine. Why is that? Well, because it's smaller, so it's easier for it to attract electrons into its outer shell, because the nucleus is closer and there's less shielding. Probably a good idea to mention shielding. Okay. Or they do say reactivity here. You can say that, well, iodine is less reactive than bromine and bromine is less reactive than chlorine, rather than saying that, phrasing it in terms of being oxidizing agents. Right, okay, so there's questions not much above GCSE content really. Okay, chlorine is used in water treatment. One benefit and one risk. Well, benefit is that it kills harmful microbes. And the risk is that chlorine is toxic. So you've got to get the concentration right. Toxic to human beings. Right. Here we've got a compound containing bromine and fluorine only, and it's got a boiling point of 41 degrees C. Okay, so how are we going to do this? We've got 1.6 grams of the compound is heated to 80 degrees C, so it will boil and it will make a gas, and it gives you the volume of the gas. Okay, now they tell us 1 mole of gas occupies 29 dm cubed under these conditions, so we're going to write down the moles is equal to the volume in dm cubed divided by 29. Okay, right, so we need to work out how many moles we've got. Well, we've got 0.209 dm cubed divided by 29. That is equal to 7.21 times 10 to the minus 3 moles of the compound A. Right, now we know that here moles is equal to mass over mR. We want to work out the mR of this gas because we want to work out the molecular formula. So let's rearrange that. We get mR is equal to mass over moles. They tell us the mass of this gas is 1.26 grams. And the moles we just worked out is 7.21 times 10 to the minus 3. So that equals, that gives us 174.8. Okay, now that is the MR of the gas, and it's only got bromine and fluorine in it. Bromine has got an AR of 79.9, and fluorine has got an AR of 19.0. Okay. Now we've got to somehow add those up together to get 174.5. Well, if you mess about with it, I think you'll find that the only thing that works is BRF5. That has got an MR of that much. Okay, and bromine could do that. Bromine is going to have an oxidation state of +5 in that, which is fine. Bromine quite often has that. The bonding, there should be no problem with bonding in that molecule. Okay, so that's what we've got, BRF5. That's the molecular formula. Right, more inorganic now, transition metals. Okay, now let's have a look at this. Right, so we are adding ammonia. Now, ammonia it acts as a base with transition metals. So we're going to have these transition metals. We've got, let's say, H2O 6, it could be 2+ or 3+, let's call it X+. Okay, so we've got the, if you add ammonia to that, what it will do, it will act as a base. It can act as a base. It removes protons from the water, and so it turns those into the waters into hydroxide ions, and so the ion becomes uncharged overall. Let's say if that was a 2+, it'd be that, yeah, and you get a precipitate. And then sometimes with certain things, you add excess, then you get ligand exchange reactions, and you can replace those waters and the OHs. If you add excess ammonia, concentrated ammonia, you'll replace them with ammonia ligands, usually 6 of them. Okay, so that's what we're looking for. Now, let's look at C. Now, first of all, you get a gray-green precipitate. That is the that's got to be, that sounds like the chromium precipitate. Yeah, and when you add an excess, it redissolves and makes purple solution. That sounds like the color of the complex chromium forms of ammonia. So I think we can safely say that C contains chromium 3+ ions, right? And we need to construct ionic equations for the formation of products D to H. So let's do, first of all, let's do this E. So we're going to have chromium H2O 6, and that's going to be a 3+, and we're going to remove 3 H+ from that, so we're going to need 3 ammonias first of all, and we're going to form this, which is the gray-green precipitate, and that's no charge, and that is actually E. That's compound E. And we're going to make get 3 ammonium ions on this side of the equation. Right, now how does, then we add excess, we're going to form the purple solution F from E. So let's do that now. So we've got chromium H2O 3 OH 3. We're going to need 6 NH3s to push all of those out. We form that, which is purple, this complex, that's 3+, and that is F. And to balance that, we need to have 3 waters coming off, 3 of those water ligands, and 3 OH minus is coming off as well. Okay, so that is our equation. That's forming E and F. Now, let's look at B. When you add ammonia to that, all that happens is you get a green precipitate. And that sounds like Fe2 plus to me. And then no further change occurs when you add excess. The Fe2 plus doesn't form a complex with ammonia. So let's show the formation of precipitate D from B. So B contains, I'm pretty sure that contains Fe2 plus ions. Okay, so let's do B. So we've got Fe H2O 6 2 plus. We're going to have just 2 NH3s there. We're going to remove 2 protons. We've got Fe H2O 4 OH twice. No charge on that. And we formed 2 ammonium ions there. And that's the end of that. And that one is, that's complex D. Okay, right. I'm going to rub all this out now, I think. Do the next bit. Okay, let's see, let's get got rid of that. Okay, let's do the next bit now. So now we're adding bit of nitric acid followed by barium nitrate. Now this sounds like they're testing for sulfate ions here, isn't it? Yeah. And yeah, you get a white precipitate with this one. So we must have a no, and we don't get anything with the chromium one. So the negative ion and the ion thing has got to be a sulfate ion. Ionic equations for D to G, right? D, G, H, yeah, we have to do that as well. So we're going to get Ba2 plus in aqueous solution plus sulfate ions in aqueous solution goes to barium sulfate solid. That's your precipitate. And there's no sulfate ions in C, but in C, what they're testing for here is that we've got nitric acid, first of all, to acidify, and then silver nitrate. We're testing for halide ions here, and you get a white precipitate. So that suggests it's the chloride ion. So we've got chloride ions in that one there. We've got sulfate ions in that one. So let's do the equation there. So you're going to have Ag plus an aqueous solution plus chloride ions, aqueous solution goes to give you AgCl solid. Okay, so that is precipitate H, and I should have said earlier, this one is precipitate G, isn't it? This one here, this is G. Right, so we have to say what was B and what was C. So B must have been an aqueous solution of iron sulfate. And C was chromium chloride. And that's that. Okay, another complex here now. Right, we've got a compound of nickel with this formula. Right, it's got the thiocyanate ions, and we've got NH3 ligands. Okay, so and it gives the percentage by mass of just 3 of the elements, so we can work out the ratio of those elements. So let's do that. So we know in 100 grams, we're going to have 16.26 grams of nickel. We're going to have the sulfur, we're going to have 35.56 grams, and the nitrogen, we are going to have 31 grams. Okay, so we need to work out the moles of each, which is mass over AR. So that's going to be 16.26. The atomic mass of nickel is nickel's 58.7. Sulfur's 31.1. 32.1, sorry, and nitrogen is 14.0. Okay, so that gives us That works out to be 1.1077. Here's the ratio. 1 of that one to, sorry, that's 0.2. The wrong one there. That's 0.277 moles of that. That gives us 1.1077 of sulfur, and it gives us 2.214 moles of nitrogen. Right, we're going to simplify that ratio. We're going to divide by the smallest number, which is 0.277. So we do that, divide that by 0.277, that by 0.277, and that by 0.277. Right, that gives us 1 to 4 to 8. Okay, so that's our ratio of nickel to sulfur to nitrogen. Right, so that lets us, we've got one nickel ion there. That's one nickel in there. Well, that means the number of thiocyanate ligands we've got, well, we must have 4 of them. Okay, so X is equal to 4. Right, so we've got Ni, let's write it down, let's write down the full formula. So we've got NH4 twice, Ni, one of them. Thiocyanate, we're going to have 4 of those. NH3, we don't know how many of them we want to find out why. Okay, so the brackets around this. Okay, so we know, right, how many nitrogens have we got here? We've got 2 there. We've got 4 in the thiocyanate, makes 6. But we've got 8 nitrogens altogether, so that means we must have 2 of those, 2 ammonias there. So Y has got to be equal to 2. So we've worked out the formula of that compound. Now it says determine the oxidation number of nickel in compound J. How are we going to do that? Well, we've got this this complex here. Right, let's do it here and tidy that up. So we're going to have 4 there. That is the full formula of the complex. Right, now we have got the ammonium ion has got a charge of +1. We've got 2 of those, so that means this nickel species must have a charge of 2+ overall. Sorry, 2-, beg your pardon, 2-. That's got to be 2- overall. Now we know the thiocyanate, the ammonia ligands, these ones have no charge, so forget about those. Each one of those is a minus, so there's 4- there. So we've got 4- and something here gives us 2-. So that means the nickel must be the +2 ion. Okay, so the oxidation state of nickel is +2. That is our answer. Okay, and this is the final question on the paper. It's a titration. Okay, so what's going on here then? Right, let's draw some little pictures. We've got a load of burger meat, and that's been extracted. We've got, how much of that was there? There was 525 grams of that. And this is in a solution, and we've got these sulfite ions, SO3 2-. Right, that then is made up into a volumetric of 250. And as usual, they only take 25 out of that, a tenth of it for the titration. Okay, so that goes into a conical flask. And then we're going to titrate that against manganate in our burette. So there's our manganate. There's our conical flask, 25 centimeters cubed in it. The manganate, oh dear, I need to do that. I've lost it. coming back. There we go. Got it back. Right. Okay. How much manganate we got there then? Okay. Well, it tells us that the concentration of the manganate is, it says it's 0.01 somewhere. Where does it say that? There we go. The 0.01 mole per decimeter cubed. And we need 12.6 centimeters cubed of that. Okay, so let's work out our moles of manganate. Concentration times volume. Concentration 0.01 multiplied by 12.6 over 1,000 gives us 1.26 times 10 to the minus 4. Now we can see from the equation that 2 moles of manganate react with 5 moles of the sulfite. So our moles of sulfite then, and that's in 25 centimeters cubed. In 25 centimeters cubed is equal to 1.26 times 10 to the minus 4 multiplied by 5 over 2, which gives us 1.26 times, that's 3.15 times 10 to the minus 3 moles of that. That's a 3 there. Sorry, that's a 4 times 10 to the minus 4. So now we need to, in 250, what is that going to be? Multiply it by 10. So moles in 250 is equal to 3.15 times 10 to the minus 3, just multiplied it by 10. That's our moles of that. Okay, now that comes as sodium sulfate. We want to work out the mass of that, so we need to know the MR. So the MR of that, it works out to be 126.1. So what is going to be our mass of sodium sulfate? It's going to be moles times MR, which is 3.15 times 10 to the minus 3 multiplied by the MR, which is 126.1. That gives us 0.75, sorry, that gives us 0.397 grams, okay? Right, that came from how much meat? That came from 525 grams, okay? So we've got 0.397 grams in 525 grams of meat. That's equal to 0.525 kilograms. So what is the mass in 1 kilogram? Is going to be, well, that's going to be 0.397 divided by the mass in kilograms, which is 0.525. And that gives us 0.756 grams. Now it tells us in the question, I think it says 800 and you're allowed 850 milligrams per kilogram. Okay. That's allowed. What have we got? Well, we've got 0.756 grams. That's equal to 756 milligrams in 1 kilogram. which is less than the 850. So that is within the acceptable range. Okay, so that is the last question on the paper. That is the end of the paper.